I mean, let's pose a question first. No, let's first give the definition of a module. Then so let R be a commutative ring with unity and M be abelian group. Such that the following those who have studied group action, you will probably recall something like that. Like G was a set acting on G was a group acting on a set X. This is similarly a ring action on an abelian group. Okay. So ring action by R. And let's write down the conditions. So it will be written as R dot M. Okay. We may call the elements of R to be scalars. Okay. So first we have 0 dot M will be 0. Next we have 1 dot M will be M for all n. Some obvious conditions as you may see. There is nothing, I mean, no condition is there which is not obvious. I mean, the conditions that should be there are there. Okay. Is there any other condition? Hello?
আমার আপত্তি আছে ডেফিনেশনে।
বলো।
তিনের কন্ডিশনটা এককে ইমপ্লাই করে। তো
রাইট।
একটা লেখার কোনো দরকার নেই। আর একটা হচ্ছে যে R1 R2 into M equal to R1 into R2M, এটা একটা কন্ডিশন।
So you see what he is saying, what Ripon is saying is that you put this and you will get back to this. Okay. So don't write this thing. So drop the first condition. Okay. So be it. And next he is talking about associativity. Okay. So these are precisely the conditions. Look at this thing. I mean, this is very similar to a vector space structure on V, right?
ডেফিনেশনটা কমপ্লিট করো
কোথায় রে?
যে such that the map satisfies blah 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 condition, then we say M is a lift R module.
Okay, okay. So I didn't complete the sentence actually. Such that the map following conditions. Then we say that M is an lifter. See, because the multiplication is being done from right, okay? The multiplication is being done from right, but we can actually drop this word left because throughout our discussion, we will only write the scalars, at the left side, okay? So there won't be a case of right R module. Clear? There won't be a case of right R module. Throughout our discussion, we will only do things as, when the scalar is written at the left side. So I will keep it thing under another line. Okay. Okay. So yeah. So one obvious thing you need to observe, just observation. If K is a field, then M becomes then a K module. M is basically a K vector space. Okay, that is the first thing you notice. It is very similar to like a vector space structure. Observation 2. What was I about? Okay, maybe we should not observation 2. Let's first give it. The example is basically our observation. Okay. So this observation 1, you can take it as example 1 as well. Okay. So example 1. Any abelian group G is a Z mode. You can check it. This is not very difficult. These conditions, you see that these are all, good enough. So you can just check this map like G to G, take N and small g, send it to NG, which is nothing but what? So you will see that all these will fall into place. Okay. So this is the first module we come across. Also, since M was taken to be an abelian group in the first place, so basically any module has a Z module structure. Okay. But don't think that R is always Z. Don't think that. And we will soon show you something. Okay. When we go to morphisms, we will show you that. Okay, let's. When we go to module homomorphisms, we will show you that how a group homomorphism is basically a Z module homomorphism. Okay, the next thing, the next example I want to give is that let V be a finite dimensional vector space over Q. You know what is Kx, right? And T okay. The polynomial ring over R, okay? You take X here, you take small v here, you will send it to what? T of v, okay? That is the action. Like the multiplication x into v is defined to be T of v. So in the same manner, so similarly, we can extend this definition, right? So for any polynomial, will be defined to be what? Okay. So
এক্সট্রা ক্যাপিটালে লেখো আর তাহলে
oh
ব্র্যাকেটটা
right, right.
আর ব্র্যাকেটটা হচ্ছে তাহলে সবার বাইরে দাও ওই A0I থেকে ANTN অবধি A0I থেকে ANTN
No, I have applied it. Oh, sorry.
তাহলে প্রত্যেকটাই লাগাতে হবে
Sorry. Yeah, I have applied it. So if you regard it as fx, then fx dot v will be f of t applied at v. So f of t applied at v. Okay. See, please don't tell me to check every detail here. I hope you can figure this out. I mean, take fx, take gx, and take everything. Okay. Check that this is indeed a module. Does v is a X module via T. Okay. We will need this thing when we go to conclude this course. At the very end of the module theory course, we will use this example to prove the primary decomposition of V. Okay. Next example. Let's give you some obvious examples first. So for any n belongs to natural number, r to the power n, not real, just for the commutative ring with infinity. When I don't specify R as a non-commutative ring, we are taking are with a commutative ring with unity. Okay, clear? Ripon,
হুম,
should I define the morphisms first, then go
একদম
to linear?
একদম
No, no.
একদম
I mean, no, 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 no. I mean, what I want to say is that why should we need modules? So I will go back to the existence of basis. So I mean, first define linearly independent sets on a module? Yes,
না,
maybe.
প্রথমে অবজেক্ট ডিফাইন করো, তারপরে মরফিজম ডিফাইন করো, মরফিজম ডিফাইন করার পরে সেখান থেকে সাব মডিউল, সাব মডিউল থেকে তারপরে তুমি আলাদা হয়ে জেনারেটিং সেট, লিনিয়ার ইন্ডিপেন্ডেন্ট সেট ইত্যাদি ইত্যাদি করে তারপরে তুমি নাকায়ামাতে যাও।
No, 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 no. What I want to say is that, I mean, the heading of the class is why do we need to study modules? So I want to show them something that we did in the vector space that cannot be done here. So that's the goal of this class.
ওকে ফাইন, আই মিন ইউ ক্যান ডু হোয়াট
Hmm.
এভার ইউ ওয়ান্ট।
But okay, when at least let's define the morphisms. I mean, he's right. I mean, whenever we have defined an object, the next thing we should be defining is the morphisms. So definition. Let M N B R modules phi M to N is called just a minute. Just a minute. Okay, I mean just in particular n equal to 1 gives us okay. Can you give me, I mean not Ripon, but you are, can you give me another obvious example of a module? Another, I mean obvious example of a module. Let's move to this definition, I mean a moment later. A very
জেড
obvious
মডিউল
example. Hmm?
সিলেক্ট ইউজ করো, বক্স করো না, সমস্যা হবে।
হুম, হুম। করছি কারণ আছে, পরের কথায় নিয়ে যাবো ওটা। কি বলছিলি লোপামুদ্রা?
জেড মডিউলের কথা বললাম।
No, no, that we have already defined. Something else? Hmm. There is a very obvious example. I mean, না, এটা লিখতেই হবে।
কিউ এর উপর কিউ সেটা হতে পারে, মানে কিউ নিজের উপরে যদি অ্যাড হয় কিউ মডিউল সেটা।
অলরেডি বলে দিয়েছি আর ইজ অ্যান আর মডিউল, তারপরে তো আর এই এক্সাম্পল গুলোর মানেই নেই।
না তুমি অবভিয়াস এক্সাম্পল বললে তো সেই জন্য বললাম।
সাবরিং নিয়ে নাও না।
হুম, এক্স্যাক্টলি, আইডিয়াল। Any ideal is an R module. Okay, let's define the morphisms. I think Ripon was right. I mean, in a way, I will have to define morphisms, then submodules before we can go into the question. I mean, I will have to give you the context at least. I mean, Ripon is always right, you know. It's called an R module homomorphism if so it will have to respect the addition, nothing. That's it. It will have to respect the addition, and by that I mean so phi R1 plus R2M. Okay. Do we need anything else, or this is just enough? The additivity is needed actually. The addition is needed. So just like the vector spaces, okay.
আচ্ছা বলছি যে ওই ফাই এর আগে লেখো এ ম্যাপ ফাই এম টু এন।
I was about to write a group homomorphism phi. I mean that I didn't write probably. Is that obvious? Yes, it is 1 times m phi m plus, yeah, it is obvious actually. It follows from this. Okay. Okay. So this condition will give you that this is a group homomorphism.
ফর অল আর ফর অল এম এম প্রাইম।
Ripon is very rigorous, by the way. So this is a module morphism, but I want to give you another example as well. I think should have given it a little bit before. Should I give that example? I mean, from R to us is
algebra?
yes. I'm thinking, or will it be too much?
না অ্যালজেব্রাটা আগে দিতে পারো।
Hmm. Okay, so you have attended the ring theory course, I think. So let's define this. I think so. This is example 6. So let R S be two rings. Whenever I mentioned anything, it is commutative ring with identity. And psi ring homomorphism. We want to view is our module via. So let's define it. So from R cross S to S, so you have R here, you have S here. How will you define the product? You define it as psi R times S. You see the product is defined because psi R is inside S, okay? And you will see that this definition will satisfy each of these axioms. Okay, so in this way you can see R S as an R module. Okay, in this particular case, the R module S is called an R algebra. So whenever we say algebra, it means that it has a module structure. You see, S has a module structure, but S is also a ring. Okay, so any R is an R algebra. I mean, that's a given. Via this identity, then psi is identity basically. So this, okay, let's get back to this definition. So this is a definition of a R module homomorphism. Okay, as you can see that this is a group homomorphism, right? So example 1, let G be an let G be an abelian group. Okay, then in then any group homomorphism phi from G to G prime is a Z module morphism. You can check that. phi g plus g prime will be, so you have phi g plus g that is phi g and of course, I mean, this is, I mean, any module morphism is basically a group homomorphism, so that part is satisfied. Let me give you another example and then we will move on to the submodules. Okay. What I was, yeah, so define phi. So you have R and M already. Okay. R and M. You will realize that this scalar multiplication by R, phi R, is an R module morphism. Okay, when I say morphism, I mean it is homomorphism basically. Okay, I'm writing it in a categorical language basically. And I should write homomorphism. When we are talking about topological spaces, this morphism will be continuous now, but please just wait. So this was example 2. Okay. So we have defined an object module. We have defined, I mean, sort of morphisms between two objects. When we say morphism, so in set you have functions, right? When set is the object, the morphisms we are talking about, I mean, set by morphisms you may think about functions. Okay. So from set to set we have functions. From topological space to topological spaces we have continuous functions. So in rings we have ring homomorphism, groups we have group homomorphism. So in a module we have, I mean, in vector spaces we have linear maps. You see, whenever we have an object, the very next thing we define is how maps between those objects look like. So morphisms we have defined R module homomorphisms. The next thing we are going to do is that what do we define after group? Subgroup. After ring, subring and ideals. After vector spaces, subspaces. So using that particular chronology as Ripon was referring to, let's define submodules.
আচ্ছা এখানে আমি একটু কমেন্ট অ্যাড করতে চাই।
করে দে।
ওই যে তুমি যে এখানে অ্যালজেব্রা ডেফিনেশনটা দিয়েছো, এই কি বলে আর আর থেকে এস যদি একটা আর অ্যালজেব্রা হয় তাহলে আর কে অ্যাজ আর মডিউল স্ট্রাকচার আর এস কে একটা আর মডিউল স্ট্রাকচার হিসেবে দেখলে ওই 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 সাই ম্যাপটা একটা মডিউল
ইয়েস, ভেরি গুড।
এটা এটা একটা আছে। এবং দ্বিতীয় কথা হচ্ছে যখন তুমি মরফিজম ডিফাইন করেছো তখন তোমাকে ইমেজ সাই এবং কার্নেল ডিফাইন করতে হবে। আর হচ্ছে কি
that I will do after after defining the submodules.
আর আইসোমরফিজম ডিফাইন করতে হবে।
I will do that after the, I mean, once I but yes, image psi and car psi will be submodule. Okay, so you want to define it just, then we will later come. Okay, first make the first comment. কি? So one thing Ripon was saying is that
আর অভিরূপ দা এখানে আর ডট এস ইকুয়াল টু মানে এস ইকুয়াল টু সাই আর, তাই তো? মানে মানে সাম আর ওয়ান।
না না, এটা মুছে গেছে, তো লিখেছিলাম, মুছলো কি করে? যাই,
আচ্ছা,
I wrote this, I mean somehow this got erased. Okay, next, if we considering both R and S as R algebras, this map psi, the map psi R to S becomes a so next let's define image and kernel. Image and kernel of an R module so as you may think, it is just same as maps, I mean just as set functions. So if phi m to n is an R module we define im phi okay. It can be denoted by phi m. Okay, it's just the image, I mean set theoretically. And kernel I mean, that should be pretty obvious as well. Okay. Next, we will have to talk about another definition, submodules. So again, M R module, okay? Even if I forget to write this, I mean, it should be clear enough then that R is a commutative ring with unity unless we mention otherwise, and M is an R module. Submodules M to R, then what? Yeah, R module submodule is basically as you might expect. So M prime subset of M is said to be an R submodule of M if M prime itself is an R module. Okay. Again a definition. Again M R module, that thing is common. So S is any subset of M, okay? Any subset. S is any subset of M, okay? We define span S in the following. What? So you take this. So you see what we are doing. We are taking vectors from S. We are taking their finite linear combinations and we are making a collection. That is called the span S, okay? It will be denoted by this notice. Okay? Check that. Ripon, this time you didn't notice it. M prime cannot be phi, right?
What? Which one? না আমি
M prime.
কিছু কমেন্ট আমি এখানে কমেন্ট করিনি কিন্তু এখানে কমেন্টটা করা যায় এরকম যে এম প্রাইমের কিন্তু আরো অনেক আর মডিউল স্ট্রাকচার থাকতে পারে
Yes, yes, yes. I was
কিন্তু
thinking
সেই
that
জন্য
it
তোমাকে
has
বলতে
to
হবে
it
যে
has
ওই
to inherit the
রেস্ট্রিকশন ম্যাপ
structure
গুলো
from him. Hmm.
ওই রেস্ট্রিকশন ম্যাপ গুলো যদি এম প্রাইম কে মডিউল স্ট্রাকচার দেয় তবে ওটাকে সাব মডিউল বলা হবে
Yes, actually, so Ripone has pointed out a very good thing. I mean, I was even thinking that while writing it. I mean, M prime can have 1,000 R module structure, but what I'm thinking is that এটা বললে মানুষজন এই মুহূর্তে কনফিউজ না হয়ে যায়, মানে আই মিন দ্যাট ইজ দি অনলি থিং আই এম কনসার্নড অ্যাবাউট, দ্যাটস ওয়াই আই ডিডন্ট মেনশন ইট।
না না, তুমি এরকম লেখো যে সাব মডিউল বলা হবে যদি
ওকে,
ওই
লেটস রেস্ট্রিক্ট থিটা, দ্যাটস দ্য বেস্ট থিং।
হ্যাঁ হ্যাঁ অ্যাডিশনটা আর ওই থিটাটাকে রেস্ট্রিক্ট করলে।
No, theta has the addition actually, because if you take 1, I mean, sorry, if you take r equals to 1, then theta captures the module, I mean the addition structure. Okay, so since it is a r module via theta, that is you remember the map theta, we are talking about this theta here, theta restricted to r cross m prime gives the module, জাস্ট কনফিউজ হয়ে না যায় লোকে, সেই কারণে ভাবছি মডিউল স্ট্রাকচার gives the module structure 1 and
আরে বাবা, লোকজন তো সাবস্পেস পড়েছে, তাহলে কনফিউজ হওয়ার কি আছে?
no, not about this, I mean they will probably be thinking why do we need this, because when we talk about subspaces we don't necessarily talk about how a single field can give different structures. I mean that thing we don't encounter in a linear algebra course. Okay, so just just take this definition for the time being. Think about it actually. Okay, let's just give you this thing. So you see, this S already has an S module structure, right? Already has an S module structure, right? And this R, I mean, then we are giving S an R module structure, right? So a same S, you see, they are having different structure. Similarly, a same ring over the same abelian group, I mean a same abelian group over a same ring can have different group structure. You can define this. Yes, why not? Take this example. So you see, V is a kx module via T, right? If you replace this T by some other linear map T prime, then V will have some other module structure via the same ring. You understand that? So V will be kx module, but not via T, but via T prime. So you see, the set is same, the abelian group, the ring is same, but they are having different module structures. So Ripon was saying that M has a module structure, R module structure, and M prime has an R module structure as well, but they should be compatible with each other. So when we have defined the map from R cross M to M, that was the ring action. So the module structure over R prime over M prime has to be the restriction map. He is one of our ex-students, I mean alumni in ISI actually, ISI Kolkata. Check that. 1. Im phi, car phi are submodules of M. 2. This is spanning set, okay? I know my handwriting is horrible. Then what? Uh, then, hmm. Then let's talk about monomorphisms and epimorphisms. Okay. If car phi is 0, phi is and clearly phi m is n. I mean, if phi m is, I mean, if im phi is the whole, if im phi is, then of course phi is surjective. That's not an issue either. I mean, this is called probably monomorphism. This is called epimorphism. Okay. I put an exclamation mark here. Let me tell you why. It is clear that phi is bijective, right? I mean, from these two conditions, it is clear that phi is bijective. But normally, when we think about isomorphisms, there has to be an inverse, right? So, thus, there exists psi from n to m, which is a set map, which is just a set map for the time being. You understand? So phi has an inverse psi. But in what, I mean, in what sense? It's a set theoretic bijection we are talking about, because injective surjective is a set theoretic bijection. But is psi an R module homomorphism? So this is your homework. See, this is a serious course. Okay, this is for M-Math and PhD students. If you are not able to check these things, I mean, then it's okay. But if you are not trying, or if you are not willing enough to check these things, then don't attend this course. It's as simple as that. Do not expect me to spoon feed things to you. Already, I think I'm diluting this content enough. But those checks, I mean, which I'm leaving to you, you should be good enough at least to try it. So isn't it a natural question? I mean, psi is the inverse map, but that's a set theoretic inverse. I mean, like a continuous map has a bijection, suppose an injective continuous map, but is it a is it continuous as well? What is psi or module homomorphism? Okay. Now let's go back to the definition again. Linear independence. If you sit and read these notes, believe me, this check, this homework, all the checks that I have given you, they all combined shouldn't take more than 30 minutes. Believe me. Linear independence. So let is any subset of M. Okay? Finite subset. Finite subset. So S has suppose this form. K belongs to natural number. S is said to be linearly independent if for any R linear combination summation Ri Mi 0 implies Ri is 0 for just like the vector spaces. Okay, just like the vector spaces. Now we drop the finiteness. Okay, now we drop the finiteness. Is said to be just give me a moment. Okay, let's just complete the definition, then I will take some water. Now, is be any subset is said to be linearly independent if any finite subset is prime of S is linearly independent. Clear? So just like vector spaces, an arbitrary set is said to be linearly independent if its every finite subset is linearly independent. Okay? Now I think is the time to pose the question. First, we have studied vector spaces. This is question 1. I mean, why do we need modules? I mean, or maybe I should write, I mean, what is special? Okay, let's just write why. Two, the definition of linear independent in a k vector space V and an R module M same. I mean, I put this word same. If you want to just go through the notes for 5 minutes, you may take it. But I want you to think about this question. Chandri, do you need 5 minutes to look at these notes? I mean, everything is given there. Just look at this thing, the definition of linear independence, and then think about this question. এই কথা কি শোনা যাচ্ছে না? হ্যালো,
যাচ্ছে।
Okay. In the first linear algebra class, I think Onjil Rohan was there, Lopamutra was there. So let's first do question 2. That will help you to understand question 1 actually. So in a K vector space V, S is a subset of V. Suppose, I mean, take S to be finite even. So if S is linearly dependent then there exists lambda I belongs to K such that summation lambda I Vi is 0, but not all lambda i's are 0. Okay. So without loss of generality, let lambda 1 is non-zero. So you can just write lambda 1 v1 is minus summation I running from 2 to n summation lambda I vi, that is v1 equals to summation lambda I by lambda 1, right? So you see, we are observing a very clear thing, that the word dependent is actually literally established, right? So v1 can be written in terms of, v1 can be written in terms of v2 to vn, right? So v1 is indeed dependent on v2 to vn. I mean, I'm talking about literal sense, not mathematically. So these two statements are equal. So statement 1, say p1, and that is this definition of linear independence. Okay, let's call this definition, I mean this definition of linear independence, I mean let's call this definition star. Okay, I mean the usual definition, I mean that if a linear combination is 0, then every vector is 0. Okay, definition star. And statement p2, সেটা হচ্ছে যে s, I'm talking about finite subsets. Okay, let's talk about finite subsets. So we have already taken s to be v1 to v. S is linearly independent if no vector in S is a linear combination of the others. So you see, P1 and P2, right? In a vector space, right? But what about modules? What do you think? Are these two same? What do you think? Okay. Hmm. It is not the case with modules, okay? It is not the case. Okay. So you see, take this set. Is not linearly independent, right? Since you have 2 into 3 minus 3 into 2 equals to 0. So you have a linear combination, a non-zero linear combination summing up to 0. So it is not linearly independent. but they are not dependent. I mean, I when I write dependent, I write this thing, I mean, literal sense. We we cannot express one of two, three in terms of the other in Z. That's the most important thing. Okay. So you see, you can write, so you can write 2 equal to 2 by 3 into 3, or 3 equal to 3 by 2 into 2. But these things, they are not in Z. Okay. In Q, they are linearly independent, but not in Z. So they are scalar multiples of each other, but those scalars are not in the ring anymore. So you see how this is different, and co- as a consequence, as a consequence, as a consequence, we cannot extend a linearly independent set to a basis in a module. We cannot, we may not, I should write. Because I mean, vector space is also a module actually. We may not extend, we may not be able to extend a linearly independent set to a again, you take the above example. Let R equals to M equals to Z. Okay. So any singleton set is linearly independent. You can understand that. So like is linearly independent, right? Right? Since A into 2 equals to 0 implies A equal to 0. So this is linearly independent. But can you take it? I mean, can you extend it? So if we take and M outside of span S, okay, outside of this thing, which is basically 2Z. Okay, so what will M be? M be odd? Right? But you see the same problem. You cannot extend it. This set this is linearly dependent. So that was not the case, right? Once you took a vector outside of the span of a particular set, it was linearly independent in a vector space. That's why you could extend the basis. So basis extension is not here. Okay. Clear? So I will end this class with a note. Let me arrow here. Okay. The power of division is there in a field, or maybe that is what enables us to extend any linearly independent set to a basis in a vector space. So I will tell you this step. Let me one, okay, tell this step as shown in one. Okay, that's it for today. We will see you in the next class. Okay,
অভিরূপ দা,
বলো।
একটা জিনিস, তখন রিপোনা তুমি যেটা বলছিলে ওই একদম ফার্স্ট এরিয়াতে এক্সাম্পলটায় যাও, যে ভেক্টর স্পেস দিয়ে যেটা কেএক্স দিয়ে যেটা দিচ্ছিল।
কোথায় গেল? চলে গেল কোথায়?
এই তো, এই তো, হ্যাঁ। এখানে ওটা তখন কি বললে যে টিটাকে চেঞ্জ করলে,
If you change t by t prime, okay.
আচ্ছা মানে
So
অন্য একটা
kx,
linear
yes,
value
yes.
নিচ্ছি, দিয়ে
If
ওই
you take
linear
any other linear map between V to V, the ring is same, the
but
abelian group V is same, but the module structure is different.
ওকে ওকে ওকে।
Okay, that's it. I will send you the note.
তো যেও না,
হ্যাঁ,
যেও না, কথা
কি
আছে,
কেন?
কথা আছে।
ক্লাসটা শেষ করি নাকি?
শেষ করে দাও, তুমি মিটিং লিভ করো না।
হুম।